Our next technique for evaluating limits algebraically is dividing out. Now, as we said before, whenever you are evaluating a limit algebraically, always begin by trying direct substitution. Again, always begin by trying direct substitution. And if direct substitution gives you a real number, that is your solution. However, if direct substitution yields the indeterminate quotient, that is the name of this, 0 divided by 0, okay, 0 divided by 0 is called an indeterminate quotient, this is a sign that we need to try another technique. If dealing with a rational function, meaning that we have a polynomial divided by another polynomial, we want to divide out. Here's our first example. Evaluate the following limit algebraically. We have the limit as x approaches 2 of x squared plus 2x minus 8 divided by x minus 2. Well, again, we always start off with direct substitution. And if I plug in 2 for x, that gives me 4 plus 4 minus 8 is 0 divided by 0. Direct substitution yields 0 divided by 0. That is an indeterminate form. It is called an indeterminate quotient, which tells us we need to do something else. Remember, we can't divide by 0, right? Dividing by 0 is undefined. So that means something special about our graph is that we actually have a discontinuity. Well, just because we have this discontinuity doesn't mean we can't evaluate our limit. So let's think about the dividing out technique. Again, we have a rational function, a polynomial divided by another polynomial. When we see this, we want to consider factoring. Notice that the numerator here factors into x plus 4 times x minus 2. So I now have the limit as x approaches 2 of x plus 4 times x minus 2 divided by x minus 2. We have a common factor of x minus 2 between the numerator and denominator, which we can divide out and simplify our limit. We now have the limit as x approaches 2 of x plus 4. And once we divide out those common factors, we can try our direct substitution again. Completing our direct substitution again gives us 2 plus 4, which is equal to 6. That is our solution. So let's take a look at this graphically. Here I have the graph of the rational function x squared plus 2x minus 8 divided by x minus 2. And notice that it actually looks like a linear function. It looks just like the linear function y equals x plus 4. Interesting there. Y equals x plus 4, except we have a hole in the graph when x equals 2. Well, just because there's a hole, that doesn't mean we can't evaluate the limit here at x equals 2. Notice that as our x values get closer and closer and closer to 2, what are the y values getting closer and closer to? My y values are getting closer and closer to 6. Right? Therefore, we can verify our solution to this limit algebraically. All right, so again, we start off by trying direct substitution. If we end up with the indeterminate quotient, 0 divided by 0, and we have a rational function, a polynomial divided by a polynomial, we want to factor the numerator and denominator, cancel out any common factors, simplify the limit, and then reevaluate using direct substitution. Right? Very important here. Notice that each one of these steps has a limit written in front of it until I actually do the direct substitution to evaluate the limit. Right? Continue to write limit until we plug in for x. Our answer then becomes a numerical value. Let's try a few more. Evaluate the following limit algebraically. We have the limit as x approaches 4 of 4 minus x divided by x squared minus 16. We start off with our direct substitution, and direct substitution yields the indeterminate form 0 divided by 0. That tells us we need to do something else. Well, we have a rational function, a polynomial divided by a polynomial. So we want to consider factoring. Notice that the denominator in this case factors into x plus 4 times x minus 4. Now, with rational functions, 0 over 0 guarantees that I have a common factor between the numerator and denominator. I have to have a factor that cancels out. This isn't as obvious right away. However, if we look at the numerator and we factor out a -1 from each of these terms, we can actually rewrite the numerator as -1 times the quantity x minus 4, right? Check by redistributing. -1 times x, that gives me a negative x. -1 times -4, that gives me a positive 4. All right, so we can factor out a factor of -1 from the numerator, and now we can see this common factor of x minus 4 between the numerator and the denominator. So we factor, now we divide out those common factors of x minus 4. We simplify the limit. We now have the limit as x approaches 4 of -1 divided by x plus 4, and now we can try our direct substitution again. In this case, we plug in 4 for x. Plugging in 4 for x gives us -1 divided by 4 plus 4, which gives us -1/8 for our answer. Again, we can always verify our work graphically. Here I have the graph of our function 4 minus x divided by x squared minus 16. It's a nice rational function. And as the x values get closer and closer to 4, the y values get closer and closer to -1/8. Again, notice we actually have a hole in the graph, all right? Whenever you're dealing with a rational function and you get 0 over 0, that means we have a hole in the graph when x equals that value, at x equals 4 in this case. All right, let's try one more here. Evaluate the following limit algebraically. The limit as x approaches 3 of 2x squared minus 5x minus 3 divided by x minus 3. Again, we always begin with direct substitution. We plug in 3 for x. Well, this would be 2 times 9, which is 18, minus 15 would be 3, minus 3 gives us 0 in the numerator, divided by 3 minus 3, 0 divided by 0. And again, we cannot divide by 0. This is an indeterminate quotient, 0 over 0. We have to do something else. Because we are dealing with a polynomial over a polynomial, we want to factor. Factor the numerator, factor the denominator, and see if we can't find a common factor. Now, if you're struggling with factoring, one thing to make note of is that if you have 0 over 0, you are guaranteed to have a common factor, in this case, of x minus 3. All right, I have to have a factor of x minus 3 in the numerator. That's the only way that I could possibly get 0 over 0 this way. Well, that can help us factoring the numerator. We see that the numerator factors into 2x plus 1 times x minus 3 divided by x minus 3. And don't be afraid to check your work by foiling. Notice if I FOIL or use the distributive property of multiplication, 2x times x, that gives me 2x squared, minus 6x plus 1x, that gives me minus 5x, and a positive 1 times a negative 3 gives me a negative 3. All right, so just double check your factoring. And we recognize that we have a common factor of x minus 3 between the numerator and the denominator. So what can we do? We divide them out, we simplify the limit, and we try our direct substitution again. In this case, we plug in 3 for x, and plugging in 3 for x gives us a final answer of 7. All right, we can check our work graphically. Here I have the function 2x squared minus 5x minus 3 divided by x minus 3. This gives us a linear function. Notice that linear function actually looks like the graph of y equals 2x plus 1, which we see right here. But it has a hole in the graph when x is equal to 3. The function is undefined. Again, 0 over 0 with rational functions means that we have a hole in the graph. But as we can tell, as the x values get closer and closer to 3 from either side of x equals 3, what are the y values getting closer and closer to? The y values get closer and closer to 7. All right, so that is the dividing out technique. Remember, always start with direct substitution. If you get 0 over 0 and you are dealing with a rational function, a polynomial divided by a polynomial, factor the numerator and denominator, divide out common factors, and then reevaluate the limit again with your direct substitution.